Welcome to the Deep Dive, your shortcut to being truly well-informed. Today, we're jumping into the online encyclopedia of integer sequences, the OEIS. It's really an incredible resource, our focus. A specific sequence, A000313. It even has this charming title, Greetings from the Online Encyclopedia of Integer Sequences. We're going to unpack this sequence today.
Right. And A000313 is interesting because it's so specific. It counts the number of permutations of length that have exactly 3 consecutive ascending pairs. So for anyone studying number theory listening, think of it like this. You're arranging numbers, say 1 to n, and looking for spots where a number is immediately followed by one that's bigger, like 2, 3, or 5, 7. This sequence counts arrangements with precisely 3 of those pairs happening right next to each other.
Got it. So a very particular constraint leading to a unique string of numbers. And the sequence starts, well, it's kind of unusual at the beginning, 0, 0, 0, then 1, 4, 30. After that, the numbers really start to take off. The entry also mentions an offset of 1/5 of 5. What's that telling us?
Ah, the offset. Yeah, that basically means the formulas associated with the sequence really kick in starting at n1. But the interesting non-zero values, the count itself, it doesn't really start until n4 based on that definition. Those initial zeros, they just mean you can't have 3 consecutive ascending pairs if you only have 1, 2, or 3 items to arrange. It's impossible. But at length 4, boom, you get that first one. That's the smallest arrangement size where it's even possible.
Okay, that makes sense. So the zeros are meaningful too. But then how do mathematicians actually figure out these numbers, especially as n gets larger? I imagine counting them by hand becomes, well, impossible fast.
Exactly. You can't just list them all out. And that's where the beauty of the OEIS entry comes in. It doesn't just list the numbers. It gives you the tools, the formulas. There are actually multiple ways to define and compute A000313, which is pretty common for sequences in the OEIS.
Right. So what kind of tools are we talking about here? How do they capture this pattern mathematically?
Well, one key thing is that A000313 is definite, which is a fancy way of saying it follows a recurrence relation. Basically, a rule that lets you calculate the next term using a fixed combination of previous terms, like a recipe. The specific rule here is mes plus 4an plus n1 n of I1 plus n-1 in ash2 an task 0.
Okay, so that gives you a way to compute step by step.
Precisely. Very useful for computation. But then there's also an explicit formula, which is quite elegant. It's an n s p n n plus 1 plus nash1 n 6. Notice the e in there, the base of the natural logarithm, and factorials.
Wow, E. That seems unexpected for a counting problem like this.
It is. It hints at deeper connections, often related to probability or asymptotic behavior. It gives you a direct way to calculate any term, an, without needing an1 or an2. And then there's also a generating function listed, EGF. It's by 33, xpx, 1 by 2. That's another powerful way to analyze sequence, especially using calculus and algebra.
So recurrence, explicit formula, generating function. Why have all 3? Don't they all just give the same numbers?
They do give the same numbers, yes, but they offer different kinds of insights. The recurrence shows the local structure, how terms depend on each other. The explicit formula often reveals global properties, like that surprising link to E, and how fast the sequence grows. And the generating function, that's like encoding the entire sequence into a single function, which you can then manipulate algebraically to find identities or connections, different tools for different jobs, you know?
Okay, that makes sense. It paints a much richer picture. Now, you mentioned connections. Is this sequence related to others in the OEIS? It feels like these things shouldn't exist in isolation.
Oh, absolutely not. The OEIS is all about connections. O000313 is linked to several others. For instance, it relates to A000166, which counts derangements permutations where nothing stays in its original spot, a classic combinatorial object. It also shows up as a diagonal in a number triangle, specifically A010027. So its terms are embedded within a larger structure. It really shows how interconnected these mathematical ideas are.
That's fascinating. It really underscores the depth here. And looking at the entry, you see the history references going back to the 60s, David, Kendall, Barton. And of course, Neil Sloan himself, the founder of OEIS, is listed as the author with contributions documented in his own handbooks from 73 and 95. It's clearly been studied for a while. The entry says it's approved and was last touched August 20, 2025. It's a living thing. So, stepping back, what's the big takeaway for you listening to this? We've looked at A000313, counting permutations with this very specific 3 ascending pairs property. What's amazing is how such a seemingly niche counting problem leads to these elegant formulas, these connections, this whole mathematical structure captured in the OEIS.
Exactly. It really highlights how defining patterns precisely, even seemingly simple ones like ascending pairs, can unlock sequences with deep mathematical properties. properties tied to fundamental constants like E, described by neat recurrence relations and connected across the mathematical landscape. So maybe the thought to leave you with is this. What other subtle patterns are out there, hiding in plain sight within simple arrangements or structures? What happens if you tweak the definition just slightly? The OEIS is full of starting points for exploring exactly those kinds of questions. Go have a look. You might find your own aha moment.